Welcome to Lecture 4.4, Sturm-Liouville theory. Let's start with the definition, which really should seem like it's coming out of left field, and in some sense it is. A Sturm-Liouville equation is a second-order ODE of the following form. So it's negative d dx of p of x y prime plus q of x y equals lambda w of x y, where these functions p, q, and w are all positive. This w is sometimes called the weighting function, and we'll see why shortly. We are usually interested in solutions, y of x, to such an equation on a bounded interval, say from a to b, under some homogeneous boundary conditions. So this is just like what we saw in the previous lecture. So this is alpha 1 y of a plus alpha 2 y prime of a equals 0, and beta 1 y of b plus beta 2 y prime of b equals 0, homogeneous because of these zeros. And these technical conditions, the sum of the squares of the alpha i's and the beta i's being positive, that's just another way to say that not both of the alphas are 0 and not both of the betas are 0. Otherwise, we have 0 equals 0. That doesn't tell us anything. Together, this boundary value problem, that is this ODE, with these boundary conditions, is called a Sturm-Liouville problem. And we sometimes write SL. We don't usually say it, though. So several comments. So this is extremely important. I know it seems kind of random right now, but my goal in this lecture is to convince you why it's so important, and I'll give you some examples as well, and we'll see more examples later. Secondly, there's a few technical conditions I won't get into involving whether this interval is bounded or non-bounded and what these coefficients can be. Sturm-Liouville problems can be regular or they can be singular. And regular problems have nicer properties than the singular ones, although this may or may not come up. It's not that big of a deal for the main ideas. Okay, here's another way to think of a Sturm-Liouville equation, which may seem like it's even further out in left field, but bear with me for a few moments. So consider the following linear differential operator L. So this is 1 over w times negative d dx times the quantity p of x d dx, this is also an operator, plus q of x. So this is a linear differential operator, and I claim that we can think of this Sturm-Liouville equation using this operator rather nicely. So here's one way to think of this, what this operator does. You can sort of peel it apart. So start with a function y, a smooth function on a, b, and apply this inner piece. So p of x d dx of y. So if you start with that, you get out p of x times y prime of x. Okay, now from here, apply the following differential operator, 1 over wx, or negative 1 over wx d dx plus q of x over w of x. If you do that, now you can do that because w is positive, then you get out this complicated thing, which is the left-hand side of the Sturm-Liouville equation divided by w of x. Okay, so why do you want to think of it this way? Well, now, this Sturm-Liouville equation is just an eigenvalue equation. In other words, Ly equals lambda y. And here's the amazing part of it. This operator, L, which is the composition of L1 and L2, is self-adjoint. So that's going to mean a lot of really nice things. In particular, the eigenvalues are going to be real, and the eigenfunctions are going to be orthogonal. And that's why we care so much about this. Then the solutions, we can construct what are basically generalized Fourier series using the solutions to these equations, and we can write any solution that satisfies these boundary conditions as an infinite sum of the eigenfunctions. That's where we're going with this. Now another way to think of this, I don't know if this is going to help at all, but I like to just show you different ways to think of this, is you can think of L as, well, you could break it up into two pieces to do the distributive law. You can say this is negative 1 over w of x d dx times p of x d dx. Think of this operator plus q of x over w of x. And it's not hard to show that this operator is self-adjoint. It's just a multiplication operator. And you can also show that this one is self-adjoint as well. So you can think of this as a sum of two self-adjoint operators. And so one way to show that this is self-adjoint is to show that both of these are individually, and this is really the only non-trivial one. Now in the next slide I will actually prove directly why this is self-adjoint. But in the process we will break this up into a sum of two integrals, and the second one will be pretty trivial. Okay, so let's formalize this. Two things. First of all, if you haven't seen this before, you're probably wondering, why the heck are we doing this? Where is this coming from? Fair question. Second thing, I was a little bit sloppy on the previous slide when I said this operator is self-adjoint. I didn't tell you what space we're talking about or what the inner product is. And we saw in the previous lecture that we can have a operator like the second derivative operator, which is self-adjoint on a vector space, but not on a different one. So formally, here's the theorem. The Sturm-Liouville operator, the same thing that we saw before, this creature, this is self-adjoint on any of these spaces, C infinity sub alpha beta on AB. So this is a space of smooth functions on A to B with boundary conditions given by the vectors alpha and beta. So this encompasses things like Dirichlet conditions and Neumann conditions and mixed conditions and all of those. And this is with respect to the following inner product. So this is, I think this is different from anything we've seen so far. F dot g, it's the integral from A to B of f of x, g of x bar, but now we multiply by this weighting function, w of x dx. So I don't think we've seen anything with a weighting function so far. Okay, so that's the inner product. Let's prove this now. As before, this is all really going to come down to integration by parts. Okay, so let's start out by writing what LF dot G is. Okay, and we're just going to use the definition. And then I'm going to show that that's equal to F dot LG. So LF dot G is the integral from A to B of G of X bar times LF times W of X dx. And that, let's copy down what this creature is. That is the integral from A to B of G of X bar, and now this LF, I want to write down what that is. So that is negative P of X F prime of X, and the derivative of that product, plus Q of X F of X and bracket dx. Okay, let's break this up into two integrals. So the first integral is, I'm going to use red for this, negative integral from A to B. So I'm just going to do the distributive property here. The first term is going to come here, so that's where the negative sign comes from. So this is G of X bar times P of X F prime of X, quantity prime dx. And then what's left over is the integral from A to B of F of X G of X bar times Q of X dx. Okay, now this first integral we want to integrate by parts. So I'm going to do that over here. I'm going to say let u be equal to G of X bar. So du is the derivative of that, which is G prime of X bar. Derivatives and complex conjugations commute. So dv, oh, let me erase that. That's minor detail. Let me put a dx after that. And then dv, so this whole thing here is going to be dv, and this thing here is going to be u. So dv is p of x f prime of x prime dx. So I should say dv, I should really include the dx. And then v is just the derivative of this, or sorry, the integral, and that cancels with the derivative, so that's just p of x f prime of x. Okay, now let's plug these back in. So this is equal to, so let's put the negative sign out front. And now let's put u times v, so the u times v, I'm gonna alphabetize these. So this is f prime of x times g of x bar times p of x from a to b, and then minus the integral from a to b of v du. So I'm also going to alphabetize this. This is f prime of x, g prime of x bar, p of x dx. So this is f prime of x, g prime of x bar, p of x dx. Okay, so this integral turns into this. Okay, now I should probably put this blue thing back here, plus the integral from a to b of f of x, g of x bar, q of x dx. Okay, now let's pause a moment and let's compute f dot lg. And then we're going to compare these two. So f dot lg is going to be similar. So it's the integral. So this proof is really just integration by parts. It's messy, but it's not that complicated. What's going to happen is basically this thing, I'll just tell you, is going to be, this term is going to be the same, this term is going to be the same, and the only difference is this term, where you swap the value of f prime and g bar, and that's going to cancel because of the boundary conditions. Okay, so the integral, so f dot lg is the integral from a to b of, now we have f of x goes here, and lg bar goes here. So it's f times the complex conjugate of lg, and then we need that weighting function, w of x dx. Okay, so this is, let's, like we did before, let's just plug L in for this. So we're going to take this LF, we're going to do the same thing here, just instead of F, we're going to have a G. So this is the integral from A to B of f of x, and now this big bracket thing, again, we're just copy pasting this thing here, but changing the f's into g's. So negative p of x g, well, I said same thing, but forgot that we got to put bars over it. So g prime of x, because we have a bar right here. So I'll put the bars over later. So let me just put this whole thing here. Prime plus q of x f of x dx. Okay, so now where do the bars go? So the bars, basically, there needs to be a bar on everything here. So now P is a real valued function, so I don't need to put a bar on that. And actually, same thing with Q. I don't think I said that previously, but yeah, I think I just said W and P are real valued, but I think Q should be real valued as well. Okay, so let's put a bar over G prime, and let's put a bar over. Oh, and I said, oh, I made a mistake here. What did I say? I said F. I forgot to change this F to a G. So I'm just going to do that. G of X, and now I'll put a bar there. Okay. Now, as before, let's break this into two parts. So, oops, let's get my pen back. So this first part is going to be F times this piece. So if we do that, we have, negative the integral from a to b of, now we have f of x times p of x g prime of x bar prime dx. So that should look familiar. That should look like that, sort of. Plus, it's not quite the same though. But now this last piece is the same. This last piece is f of x, g bar of x, q of x. That's exactly the same thing as f of x, g bar of x, q of x. So this is the integral from a to b, f of x, g of x bar, q of x dx. So notice that what I'm gonna box these things are the same. So really all we have to do is show that this integral is equal to that integral, and they're very similar. So as before, well, almost analogous to what we did before, I'm going to let this be u and let this guy be dv. So again, let u be equal to f of x, du equals f prime of x dx, and now dv equals p of x g prime of x bar. So it's this piece, and then the derivative, or the antiderivative of that, v, is just p of x g prime of x, because this derivative just cancels. Okay, so now let's write this. I'm running out of room, but I think I can squeeze this in. So this is the, so uv, this is f times p of x, g, or I should say g prime of x. I need to put a bar in there. So uv, let's see what this is. Let's write this down. F of x times g prime of x bar, p of x from a to b, minus v du. So v du, this is f prime of x, g prime of x, bar, p of x. That's exactly what we had up here. v du, f prime of x, g prime of x, bar, p of x. It's the same thing. So minus integral from a to b, f prime of x, g prime of x, p of x dx. And then plus this little integral. So integral a to b, f of x, g of x bar, q of x dx. So again, this integral that I'm boxing, this is the same, all four of these pieces. Now, this piece, that's the same here. I think I'm going to put this in a, I'm not going to box it, but I'm going to put it in like a little cloud. So this, obviously I need practice with making my clouds. So now what's left? All we have to do is show that this guy here and that guy here are the same. That's all that is left to show. So let me write that on top, and I'll put this in a different color. So let's put it up here. So need to show that f prime of x, g of x bar, p of x from a to b equals f of x, g prime of x bar, p of x from a to b. So the only difference here is, here we have f prime and g bar, and here we have f times g prime bar. And what I haven't written up, but maybe I should, I guess we didn't have room for this, is what these boundary conditions are. So these are alpha 1, so alpha 1 f of a plus alpha 2 f prime of A equals 0, and beta 1 f of B plus beta 2 f prime of B equals 0. And this doesn't only hold for f, but it also holds for g as well, because both of these are in this space of functions. So I'm actually going to leave this as an exercise because we did something basically almost exactly like this in a previous lecture. If you remember, we did integration by parts. I think it was the last lecture. It might have been one before. I've been recording a lot of these lately. But it was essentially the same thing. Remember, let me just outline how it goes. So at least one of these alphas is non-zero. So suppose alpha 2 is non-zero. Then what we can do is we can solve for f prime of A, and we can say that f prime of A equals negative alpha 1 over alpha 2 f of A. And then up in here, every time we have an f prime of A, so when we plug this in, we're going to get 6 terms, right? Let me just write that up. So I'll do one of them. So f prime of B, g of B bar, p of B minus f prime of A, g of A bar, p of A. So we want to show that that is equal to the similar thing right here. So what we do is whichever alpha is non-zero, or if both of them are non-zero, just take one of them, solve for that corresponding term, and we get that, oops, I said f prime of x, what I meant to say is f prime of A. So now, up here when we have f prime of A, we can replace that with this f of A times negative alpha 1 over alpha 2. And similarly, we can do the same thing for g prime of, which one is it? So g prime of A, over in this equation, we're going to have a g prime of A, and we can do the same thing when we have a g prime of A bar. We can replace that guy with the corresponding thing, just where this is f. So it's really exactly the same argument that we did in a previous lecture, so I'm not going to repeat it again. I think the main thing to see here is this is a self-adjoint operator with respect to this inner product, and the proof of this is basically just showing that LF.G is equal to F.LG, and what you do is you use the definition. You break it up, use integration by parts, and you get 3 terms. 2 of these, in both cases, are identical, and then the last one, they're not quite identical, but there's a lot of symmetry, and the reason why these things are the same is purely because of the boundary conditions that we impose. Okay, so I'm going to call that a proof. Again, if you want, I encourage you to check the details on this. It's great practice, and if you want to check yourself, compare it with what we did in the previous lecture. Here's the main theorem of Sturm-Liouville theory, and I really can't understate how important this is. The Sturm-Liouville problem, I'm writing it like this. So negative p of x y prime quantity prime plus q of x y equals lambda w of x y. Now this is a little bit different than how I wrote it before. When I introduced it, I divided through by the w of x, I put it on the left-hand side, and that was to show you that this problem is of the following form. L times y equals lambda y, where L was that weird linear operator. Writing it like this shows you that this is just an eigenvalue problem. What we want to do is we want to find all possible lambdas and all possible y's for which there is a solution. And it's not clear if there are any lambdas or how many there are. So you think of the lambdas as being like fundamental frequencies or nodes or modes of the system. And these things will come up all the time in physical problems in physics and engineering, and we'll see a lot of examples of this. Okay, so this Sturm-Liouville problem, subject to the homogeneous boundary conditions, that's this system involving y of a and y prime of a's, y of b and y prime of b, and these coefficients alphas and betas. We've seen that before. I think it's just easier to say, subject to the homogeneous boundary conditions. This has the following properties. First of all, it has infinitely many eigenvalues, and moreover, these eigenvalues can be arranged in increasing order so they diverge to infinity. In other words, they're unbounded. They don't converge to some limit or oscillate back and forth. Secondly, there is an orthonormal basis of eigenvectors or eigenfunctions yn, so that every smooth function on AB satisfying these boundary conditions can be written uniquely as a linear combination of these eigenfunctions. So an infinite sum, possibly infinite sum, from n equals 1 to infinity of Cn yn of x. So think of this as like a generalized Fourier series, and that's actually what they're called. Okay, so several comments about this. First of all, the proof. The proof that there are infinitely many eigenvalues is difficult. It's way beyond the scope of this class. It's advanced graduate level material. It's not something that I know how to do offhand. I could look it up and read about it and figure it out, but it's not something that most people simply know how to do. It's specialized. So I want you to take this as a fact. It's a little bit easier to show that these things I think diverge to infinity. I think you can use some sort of energy argument. If you want, you can Google that, but also beyond the scope of this class. So because the Sturm-Liouville operator, L, I guess I've erased it, L y equals lambda y, because this L is self-adjoint, we know that eigenvectors corresponding to distinct eigenvalues are orthogonal. And something else you can say is that these eigenvalues, or each eigenvalue is only going to have one eigenvector. So it's elementary. We've already shown that distinct eigenvectors or eigenfunctions are orthogonal, but it's also advanced and not clear why they actually form an orthonormal basis. In other words, why is this property true? This is also something that's beyond the scope of the class, and you could assume that it is fact. But this is why it is so important, and it all boils down to the fact of L being self-adjoint. Here's an amazing remark. Every second-order linear homogeneous ODE, something like this, y double prime plus p of x y prime plus q of x y equals 0, can be written as a Sturm-Liouville equation called its self-adjoint form. I'm not going to say too much about this, but basically this is saying that we can take a second-order ODE and we can write it so solutions to it are eigenfunctions to an equation of the form Ly equals lambda y, where L is a Sturm-Liouville operator. I guess it's not quite this thing, but it's close. And lambda are the eigenvalues. Now, this should seem very vague now. I think the best thing to say is wait until, I think, 2 lectures from now, and we will, maybe it's the next lecture. I think it's 2 lectures from now, we will do a lot of these examples. Things that actually arise in physics and engineering. Things like Chebyshev's equation, Legendre's equation, and Hermite's equation. Returning to the more immediate present, what we'll be doing in this lecture is given a Sturm-Liouville problem, say Ly equals lambda y, with boundary conditions, of course, we want to do 2 things. First of all, we need to find its eigenvalues. Find all possible lambdas. And secondly, find its eigenfunctions. So find the solutions to this ODE, and these things happen to be orthogonal. And remember, that's orthogonal with respect to the following inner product. F dot g is the integral from a to b, f of x, g of x bar, w of x dx. And once we have that, we can write any function that satisfies this ODE and these boundary conditions using these eigenfunctions in a generalized Fourier series type thing like this. So in the next lecture, we will study these generalized Fourier series and do some examples. And in the final lecture, I don't know if it's the final, but in the lecture after that, we will look at some common ODEs that come up in physics and engineering and put them in self-adjoint form and solve them and use Sturm-Liouville theory to find a basis and to construct this generalized Fourier series. Let's do some examples. And I'm calling these familiar examples because everything I'm going to show you we've actually solved before. I just want to show you how it fits into this framework. So recall that a Sturm-Liouville equation is a second order ODE of the following form. So this involves functions p and q and this weight w. And we're usually interested in solutions on a bounded interval AB under some homogeneous boundary conditions. And together this is called a Sturm-Liouville problem. We're going to finish this lecture with a series of 4 familiar examples. These are examples that we saw in detail and we actually solved them when we learned about boundary value problems in lecture 4.1. What I didn't tell you at the time is when we were finding lambda, we were secretly finding the eigenvalues to a Sturm-Liouville equation. And when we found the solutions, we were finding the eigenfunctions. Okay, so here's the first example. This is when we have Dirichlet boundary conditions on a very simple ODE, negative y double prime equals lambda y, and y of 0 equals 0, and y of L equals 0. This is a Sturm-Liouville problem. And this is easy to see by looking at the definition that this ODE is what you get when p of x equals 1, q of x equals 0, and the weighting function w of x equals 1. And the boundary conditions, these arise when alpha 1 and beta 1 are both equal to 1, and alpha 2 and beta 2 are both equal to 0. That's why these are called type 1 boundary conditions, alternatively, because the alpha and beta 1s are non-zero. Now let me say a technical point. In example 4.1, we actually made this a positive y double prime instead of a negative y double prime because it seemed natural. Why would I make it negative when that could get absorbed into the lambda? But I'm making this negative here because of the negative sign in the definition of a Sturm-Liouville equation. So when we solved this example, recall that we did 3 cases. So we had case 1 where lambda was equal to 0, case 2 where lambda was equal to omega squared, in other words it's positive, and then case 3 is when lambda was equal to negative omega squared and forcing it to be negative. And in these first 2 cases, we got no non-trivial solutions. We got that y was equal to 0. So we focused our attention in the last case. And remember, as I said before, our ODE here, it was positive y double prime equals lambda y. And I told you we had to solve for y and lambda. I didn't really tell you why. So in case 3, we got that omega was equal to negative, no, it wasn't negative. It was, omega was just plain old n pi over L, which means that lambda was negative n pi over L squared. Well, because of this negative sign, all that does is that puts a negative sign here, and that makes, if you prefer case 2, that makes this negative and case 3 positive. And so as before, omega is n pi over L, just now that the eigenvalue lambda is positive. So the eigenvalues of this Sturm-Liouville equation are n pi over L quantity squared when n is any positive integer. And the eigenfunctions are the sine waves. So yn of x is sine of omega x, where omega is n pi over L, so it's sine of n pi x over L. Example 2, the same ODE, except now we have Neumann boundary conditions. So y prime of 0 equals 0 and y prime of L equals 0. So this is a Sturm-Liouville equation for the same reason. If you look at the definition and you set p of x and w of x to 1 and q of x to 0, you get this ODE. And these boundary conditions now arise when the alpha and beta 1s are equal to 0. The alpha and beta 2s are equal to 1. So this is sometimes called a type 2 boundary conditions. The eigenvalues are just the same as in example 1, if you recall. So lambda n is n pi over L quantity squared. The only difference now is that n could be 0. And that was because the eigenfunctions are cosine. So yn of x is cosine of n pi over x. And when n is 0, you get a constant function, and that satisfies these boundary conditions. If you recall example 1, what we had functions that had to go through the origin and and intersect the y-axis at L. So we had things like sine waves. So sine of pi over L, sine of 2 pi over L, sine of 3 pi over L, and so forth. In example 2, we had cosines. The only restriction we had now is that they were flat at the boundaries rather than going through certain points. So things like a cosine wave worked, cosine of 2 pi over L, cosine of 3 pi over L, etc. And then the constant function worked as well because those were clearly flat at the endpoints. Example 3, this is when we had mixed boundary conditions. So we have the same ODE, but now we have a Dirichlet or type 1 condition on the left and a Neumann or type 2 condition on the right. This is a Sturm-Liouville equation because P, Q, and W are just as before, 1, 0, and 1. And now our alpha 1 and our beta 2, these things have to be 1. And beta 1 and alpha 2, these are equal to 0. That's how these boundary conditions arise. And if you recall, the eigenvalues were a little bit different. Now they were half integers, n plus 0.5 times pi over L, when n is any non-negative integer. So again, the difference between the first two cases is now we have, again, 0 to L, and the function must go through 0, but it must be flat at L. So we got sine waves because it goes through 0, but because they were flat at L, that's where the local max or min was, so their period was twice as long. So that's where this half integer thing arose. And the eigenfunctions, as before, remember that lambda was equal to negative omega squared, but we're going to make that positive omega squared because we added a negative sign here. And omega was what we got. Omega was n plus 1/2 times pi over L. And so the eigenfunction was yn of x is sine of omega x. So sine of n plus 0.5 pi x over L. And finally, we get to the fourth example. I think in lecture 4.1, I call these more complicated boundary conditions. They actually have a name. They're called Robin boundary conditions. The left endpoint is the same as before, but now the right endpoint is this linear combination, y of L plus y prime of L equals 0. As before, this is a Sturm-Liouville equation where p of x is 1, q of x is 0, and the weighting function w of x is 1. But now the boundary conditions arise if you set alpha 1, beta 1, and beta 2 all equal to 1. Again, the last one is because we have this linear combination, and then alpha 2 is equal to 0. You can imagine how much more complicated these boundary conditions can be. You can, instead of having 1, 1, 1, 0, you can have any 4 real numbers as long as both alphas are not 0 and both betas are not 0. The eigenvalues here, this was more complicated. We didn't get a closed form solution. What we got, if you recall, this is the one where we had that graph of the tangent function. And so to find the eigenvalues, we actually had to solve this equation. We had to find the intersection of tangent of Lx and y equals negative x. And we took the positive roots of that. And those were the omega. So this was omega 1, this was omega 2, this was omega 3, and so forth. And as before, lambda was equal to negative omega squared. So the nth eigenvalue, I didn't tell you were finding eigenvalues, I said you were finding a constant. The nth eigenvalue was the negative square of omega n. But again, because we're adding a negative sign here, that makes this positive. So the eigenvalues are lambda n is omega n squared for the positive integers, where the omega n's are the positive roots of x minus tangent of Lx. And the eigenfunctions, once again, yn of x is sine of omega nx. And Omega n, again, is nothing simple. It's the roots of x minus tangent of Lx. So what we learned today, I didn't do an example of it, but any function that satisfies this Sturm-Liouville problem, so solves the ODE and satisfies the boundary conditions, can be written. So f of x can be written uniquely as a linear combination. So Cn yn of x of the eigenfunctions. And that's a remarkable result. In the special cases of like example 1 and 2, we get Fourier series, and you've seen that before, and that's remarkable in itself. But here we get this for sine waves with these weird irrational frequencies. And this is just a really simple Sturm-Liouville equation. There are many, many more complicated ones where these solutions do not involve sines and cosines at all. Sometimes they involve things like polynomials. And still, every solution to the ODE can be written, that satisfies the boundary conditions, can be written using those eigenfunctions. So in the next lecture, we will study these things that are called generalized Fourier series. We will actually revisit these 4 examples and actually do that. We will write these functions using these sums of eigenfunctions. And then in the lecture after that, I'm going to show you some crazy Sturm-Liouville equations, things that come up in engineering and physics naturally, a few things that we'll actually see later in the class when we study PDEs. You've likely heard of them, things like Chebyshev's equation, Legendre's equation, Bessel's equation, and Hermite's equation. So we will see these ODEs. I'll show you what the solutions are, and often the solutions involve things like power series or polynomials. Looks like polynomials. And when they're polynomials, that means that we can write any solution to the ODE that satisfies the boundary conditions as an infinite sum of polynomials, of these orthogonal polynomials. And you've probably actually heard the names of these, things like Chebyshev polynomials, or Legendre polynomials, or Hermite functions. So that's where these things come from. They come from Sturm-Liouville theory, which comes from physics and engineering. So a lot more on this later in the next few lectures. It's really fun, really exciting. Stay with us.